In this video, we're going to be starting with our third of 3 AP reactions. This type is called acid-base. This video, we're just going to go over the definitions of what acids and bases are, as well as some things that we're going to need in order to be able to actually write reactions. The second video is going to be a listing of the different acid-base reaction types. Please note for the second video, I'm not going to do much in the way of solved examples, because it's all just identifying different types of patterns, and that's something that we'll save a little bit more for class. All right, so the objectives here is we want to be able to determine if something is an acid or a base. We want to be able to classify an acid or a base as strong or weak. There's going to be a little bit of memorization for you. Then the next video, we're going to talk about writing neutralization reactions, and then we're going to talk about writing proton transfer reactions in the form of net ionic equations. All right, so we will start off with a bunch of definitions. All right, so first definition for an acid is what's called the proton. Proton is H+, right? So a hydrogen without the electron. Now, one thing to keep in mind is that if you are in aqueous solution, a proton will instantly react with water to form H3O+. What this means for us is that once we start getting later on in the year, we're working more with acid-base solutions, you'll see H+ and H3O+ written almost interchangeably. Right, so that is one thing to kind of keep in mind. Now, an acid by definition is any substance that can give up or donate a proton. Right, so anything that can lose an H+ is an acid. What you learned during your first year chem class is that the formulas for acids will usually start with hydrogen. Right, so for example, hydrochloric acid HCl, sulfuric acid H2SO4. Organic acids, you'll also see their formulas written ending in COOH or CO2H, because that is the organic acid functional group. That H+, or that H on the end, is the hydrogen that actually gets lost when you form the proton. Now, if an acid can donate protons, a base has to be anything that accepts those protons. Any compound that ends in hydroxide is going to be a base. Now, using this concept of the proton and a proton being donated by an acid and going to a base gives us an example of what's called a conjugate pair. Conjugate pair is an acid or a base that differ by a single proton. Right, so as an example, acetic acid is an acid, so HC2H3O2. Right, so this is an acid. It can react to donate a proton, and that leaves C2H3O2-, which this is a base because it can accept. This acetic acid and this acetate ion are a conjugate acid-base pair, right? Because the only thing that's different about them is a hydrogen and a positive charge. This will become extremely important later on in the year when we start talking about acids and bases in depth. The last definition that we need is a strong acid or strong base. A strong substance is anything that breaks up 100% into its ions. Right, so this acetic acid right here forms H+ and acetate. This is not a strong acid. In fact, I have the reversible arrow here to show you that this is actually quite weak acid. It will break up a little bit, but not much. Right? In fact, it's only about 1 in every 1,000 molecules of acetic acid that will break up in this way. For a strong acid like HCl, HCl will completely go, so just the regular completion arrow, into H+ and Cl-, always. Right, so strong acids, 100% dissociation, weak acids, less than 100%. All right, so now for the memorization lists. Now, these aren't that bad. So your strong acids list is what we nicknamed the Big Six. So these are the only 6 strong acids we're going to work with. Hydrochloric, hydrobromic, hydroiodic. Nitric, sulfuric, and perchloric. Know these. Now, one thing to keep in mind about sulfuric acid is that it's what's called a diprotic acid. Diprotic meaning that it will lose protons twice. So what you have is you have H2SO4 will lose a proton to become HSO4 minus. Then this HSO4 minus, now I'm going to be very picky technical about the way I'm drawing this. This reaction is technically reversible here, but it's very, very, very product favored. It's so product favored that it's essentially a strong acid, like it's 99-point-something% dissociation, where it will form another H plus and SO4 2 minus. So this is an example of a diprotic acid. It reacts twice. Right, so these 6 are your 6 strong acids. Your strong bases, for right now, your strong bases are only going to be group 1 hydroxide. So lithium, sodium, potassium, cesium, rubidium hydroxide. As we go on later in the year, after we learn about like why solubility happens the way that it does, I'm going to add a couple of more strong bases to this list, basically lower half group 2. But for right now, we're just going to use group 1. All right, so those are the strong acids and strong bases. Please have them memorized. Now to get back to our conjugate pairs a little bit, I've already shown you a little bit of this, but when an acid loses a proton, it forms a base. That base is called its conjugate base. Now this is a general format reaction. HA is our generic acid, H for the acid, A is whatever negatively charged ion we attach it to. So it could be like chloride or sulfate or acetate or whatever. Right, and then you just have the ion left over as the base. Right, so the acid will dissociate to form H plus and A minus. This is a generic reaction. We'll use these a lot. When a base gains a proton, it becomes protonated, or it's what we call protonated. It forms something that's HB plus. So for example, an example of this is if I were to take, for example, a proton and react it with the weak base ammonia, we would wind up forming the conjugate acid, which is the ammonium ion. Right, so this is what I mean by that. Now, it doesn't always have a plus sign right here. You can, for example, if I were to reverse the acetic acid, so C2H3O2, and we'd form HC2H3O2. Right, this would still be our conjugate acid right here. This is the HB plus, again, because our acetate was negatively charged. Adding 1 actually cancels the charge out. Right, and this is something we're going to go much more in depth on as part of our last unit of the year, Unit 8 on acids and bases. So don't worry if it doesn't make complete sense right now. I'm just trying to introduce the topic. Aside from that, the next video is going to talk about the different reaction patterns, and I'm going to use these generic acids and bases as part of my reaction pattern. All right, so as always, if you had any questions, make sure you bring them in the class. Otherwise, I will see you guys a bit later.